I wanted to have a look at a couple more examples of vertical circular motion now that you've had a chance to try a few questions on it. There's one or two things that have come up, so just wanted to go through, as I say, a couple of examples. It's a tricky topic, this one. You do need to be quite flexible with it. So although I have a general approach, you do need to treat it with caution and make sure that you're applying it sensibly and amending it sensibly if particular questions don't seem to quite fit what you're trying to achieve with your general sort of method. So normally what I do with vertical circular motions is I start off with a a conservation of energy approach, looking at changes in kinetic energy and potential energy. Usually that's to establish something about v squared, for example. It's usually something about the speed. And what you need to be particularly careful about that, as I've mentioned before, is making sure that you're calculating or finding expressions for changes in height very carefully. So that's the first thing. My second technique would be then to look at radial forces and Newton's second law in the direction of the radius, so F equals ma in a radial direction, and that will usually lead you to something about either one of the forces or perhaps an angle or something like that. Might be when one of the forces disappears if you're looking at leaving the circle or something like that. So generally speaking, I would normally start off with energy, and then I'd have a look at forces after that. So here's the first example. Child mass 20 kilograms on the swing, 2 ropes, given a length, starting at an angle of 50 degrees. I particularly wanted to do this example because it's not starting at either the top or the bottom, although we're looking at going to the downward vertical. So, I wanted to start this. I wanted one that didn't start at either the bottom or top of the circle. Starting at an angle of 50 degrees with a downward vertical being released. The implication here, I've put it on the diagram here, the implication of it being released is that we're starting with u equals 0. A couple of modelling bits of information there as well, and essentially what we've got to do is calculate the speed at the lowest point of the swing and the tension in each of the 2 ropes at this point. So I've already got my diagram going with the basic information on it. There's one extra bit that I wanted to put on to my diagram now that I've started talking about it, and that was about the tension in the ropes. So I've got my downwards force of 20g at the bottom of the circle marked on there because I think I'm going to need that at some point. But my upwards force here is the strings, so it's a tension. There are 2 ropes, and just by a sort of symmetrical assumption about the whole problem, we'll just assume, and it's perfectly reasonable to assume, that the tensions in each of the ropes is the same. So this needs to be the upwards force here needs to be labelled as 2t, so that by the time we've answered the question about finding the tension in each of the 2 ropes, we'll be solving an equation in t, and that will be the tension in each of the 2 ropes. So just a little point there. Following my normal process, we're going to be looking at kinetic energy gained here. So KE gain, because we're going down the circle, KE gain is going to equal GPE lost. Not like a G, sorry. GPE lost. It's a bit more like a G there. We've got no kinetic energy at the starting position of the 50 degree angle. So actually all I need in my KE gain is just a half mv squared term. I don't need to worry about half mu squared term here. So half mv squared, where v is the speed at the bottom of the circle, is going to be equal to the mgh, and here in this case we need to now just think carefully about our h. What h are we going to have? So the we're looking at the change in height, so that's the gap from the green dotted line down to the base of the circle. It's that distance that we're interested in. So we've got a radius of 2.5, and then with this right angled triangle here, we're going to be looking at the vertical side is going to be the one adjacent to the 50 degree angle. So that vertical length down to the green line from the center of the circle down to the green line is going to be 2.5 cos 50, and that means that the h, the change in height here, is going to be mgh. H is now going to be 2.5. It's 2.5 minus 2.5 cos 50. So very much like the general kind of change in height thing that we've been using so far, where I've always been doing r brackets 1 minus cos theta. Same kind of thing going on here, but this time we haven't got an unknown angle in that, we've got a 50 degree angle in it. So let me make that point again. You just really need to be very careful about how you find expressions for changes in height in these problems. That tends to be the thing that gets people confused, or they have trouble with. So let's see if we can make some progress with this then. The mass is going to cancel out in this equation, so we're not going to need to worry about that one. We'll multiply both sides by 2, as we often do. So that's going to leave us with v squared being equal to 2g, and now instead of our h, we can have, and we can factorize that thing if we want to, 2.5 brackets 1 minus cos 50. Or 5g 1 minus cos 50 if you prefer. And so we've been asked to calculate the speed rather than, sometimes they just ask you for v squared. Here they have actually asked us for the speed, so we're going to need to do the square root here. So v is just going to be the square root of all of that lot. No unknowns left in there now, so it's just a straightforward calculation at that point. So we want the square root of 5g brackets 1 minus cos 50. And I got my calculator out earlier to work that one out, and it comes out, check that, but that comes out at apparently 4.1837 ... which we'll round off to 2 significant figures and get away with 3 probably, but 2 significant figures is better. 4.2, that's the speed, so that's going to be meters per second. We can ignore the possibility of the negative square root here because we're dealing with speed, and speeds can never be negative. So there we are, that's successfully achieved the speed at the lowest point. Calculate the tension in each of the 2 ropes at this point. So now this is the second technique. So we've had a look at an energy technique for that section, and now I'm going to move on and think about the Newton's second law, the radial forces, as my second part when I'm trying to calculate the tensions. So thinking about Newton's second law here, radially we're going to have I'm doing that, Newton's second law. So I want inwards forces to be positive and outwards forces to be negative. It's always that way because the acceleration is always directed towards the center of the circle. So inwards I've got 2t, outwards I've got 20G. No need to do any resolving of the weight force here because it's vertically downwards, so there's no angles, no resolving of into components needed or anything like that. So there's our resultant force, 2T minus 20G. That's our F, and that's got to be equal to MA, and we are, because we're dealing with circular motion here, the acceleration, radial acceleration, is always either v squared over r or r omega squared if you're using the rotational speed. Here we're using the linear speed v, so we're going to be doing this as mv squared over r. So 2t minus 20g equals mv squared over r. There's various bits of information we can put into that now, but essentially we've just got to solve that now for t. So let's just put some numbers in before we start doing anything else. So 2t minus 20g, nothing I can do about any about the t there because that's what we're calculating in the end. So 2t minus 20g, m we know to be 20. R we know is going to be 2.5. And v squared, we've got this expression up from the earlier part of the question for our v squared, so we'll just go for that v squared expression rather than you could use the decimalized number here, but remember if you're going to use the decimalized version to substitute in here, remember we'd need to go back to that unrounded version, not the 4.2. That would leave us with too much inaccuracy. Better to go back to the uncalculated version really, so that we've got all the possible precision. So we're going to have here 20 over 2.5 multiplying for the v squared 5g brackets 1 minus cos 50, and then that's reasonably straightforward for us to solve. We can take the 20g over the other side, we can divide everything by 2. That's going to leave us with t being equal to 10g from the half the 20g. 20 over 2.5 is going to give us 8, but we're going to halve that because of the 2t, so that's going to be a 4, but we're multiplying that by 5g, so that's now going to come up to 20g brackets 1 minus cos 50, and at that point we're ready to do the calculation. And if you, I've done this in my, we could just tidy it up a little bit. I suppose we've got a 10g and then we've got a 20g times 1 in here, haven't we? So we could just have this as 30g, and then we'd have minus 20g cos 50. Or, leave it factorized if you prefer, have it as 10g and 3 minus 2 cos 50, or whatever you like to do, whichever you think is the most efficient way to do that calculation. And if we do the calculation, as I say, I did this calculation a little bit earlier as well, that comes out as 168.01 ... And again, if we round that off to two significant figures, that's going to come to 170. This is a tension, so that's going to be a force, and therefore in newtons. And remember that that's 170 newtons in each of the two strings. So there's a reasonably straightforward, example, but not starting at either the top or bottom of the circle, starting somewhere else. I want to have a look at a second example, but I'll do that on a separate video, so that you can look at them. The other one is quite a tricky one as well. So there we are.